Hi everybody, we'll just wait another few seconds just while people are just joining the meeting. I think I see the numbers increasing on it by the second. Okay, everybody, you're very welcome to join our second session on machine learning, and this one is machine learning and insurance, general insurance reserving, and it's on method comparison and interpretation. So apologies first of all for being slightly delayed. We had some technical issues we were trying to work through before we started, but I think we're all good to go now. So just quickly run through some the normal housekeeping issues. You will hopefully are aware that once you log into this session, your CPD is automatically recorded, so there's no need to sign any forms, etc. During the course of the presentation, there is a Q&A at the bottom of the screen that people are free to use. At the end of the session, we will kind of use the raise hand function, but please don't use that while the presenters are actually speaking, and we will do that at the Q&A session at the end. And just to ensure everybody's aware that this webinar is being recorded in addition to the Q&A, but we will hopefully have that on AccuView and YouTube later on after this presentation. So just to give a quick description of what we're going to cover here, as mentioned, this is the second session in a series of 2 talks on the topic of applying machine learning techniques in general insurance reserving. This talk builds on the session we had a few weeks ago, which focused on validation, feature engineering, interpreting machine learning results, and comparing performance of traditional reserving techniques for different claims characteristics. We've got 2 speakers here, which will hopefully be a great session, and I'll introduce both of them now, and in the course of the presentation, they will switch over in midway through the session. Our first speaker is John McCarthy. John is reserving actually based at Willis Towers Watson in the UK. He's over a decade of general insurance experience, mainly covering reserving and commercial and legacy lines of business. He's volunteered with the IFOA's Machine Learning and Reserving Working Party for the last 2 years, and he's keen to use machine learning techniques to save time and sharpen the insights offered by reserving teams. John is accompanied by April Liu. April is a qualified actuary with 10 years of general insurance experience over a wide range of actuarial topics, including actuarial reserving, capital model validation, M&A diligence, and delivering large-scale transformation programs. For 4 years, she led reserving for one of the largest Lloyd's syndicates, and April has a keen interest in exploring machine learning techniques and improving insurers' operations through streamlining data systems, broadening modeling skill sets, and reconsidering the role of actuaries. So without further ado, I'll pass over to the experts in this field, and we'll start off with John.
Well, thank you for that introduction, Paul, and thank you for joining us this afternoon. So why is it that reserving teams haven't fully embraced machine learning yet? Our survey points to 2 barriers. Firstly, a lack of time, and secondly, a skills gap. If, like us, you're curious about the potential benefits of machine learning, you may have hit a stumbling block in just getting started, as there's few end-to-end examples available that cover reserving specifically. So as a starting point, our working parties looked at testing some popular machine learning methods on triangle data. The spring talk at the IFOA conference from last year gave a walkthrough of lots of different methods applied to a single triangle. Here we're going to focus in on 2 of those methods, the lasso and XGBoost, but we'll apply them to lots more triangles inspired by real-world reserving problems. There's an excellent write-up, by the way, of the spring conference talk from last year on our blog site. I've posted a link down here. So that's got all the R code that you need to get started. So definitely check that out. If you're new to machine learning, then this talk is for you. We're going to start with a recap of the framework for applying machine learning. Then we'll go through the data that we've used and high-level results. April's then going to give an extended commentary on the results using an R Shiny dashboard. and then we'll finish with next steps and Q&A. Quick note on the working party. So the working party itself is not just made up of actuaries. We also have data scientists and academics on board. It's a very active and diverse group, and volunteering has really helped me to get started in this area. I'd especially call out our blog site. There's lots of really good stuff on there. So we have some great getting started articles, which include all the code that you can copy and paste, all the way up to some pretty advanced examples setting out granular IBNR methods at the policy level. So please check that out. But our focus today is on triangles. So here's a triangle. We've got 5 accidents and 5 development periods shown here. The incremental paid is in blue, and then we're trying to predict the values in the peach cells. And this is the standard triangle setup for a reserving class. In the machine learning framework, we melt this triangle down into a data table. So now in this tabular format, you can think of each row as one observation from the population of interest. The available blue data is now called the training data, and this is going to be used to train our machine learning models. And then the data that we're trying to predict, we've still got in peach, and this is now called the test data. So just adding some notation to that table. So we label the incremental loss Y. That's usually called the target. The accident and development periods we label X, and these are usually called features. And our goal is to find a model that predicts the target well using the features as inputs. So at the end of all this, the model is just a function that takes X, the features, as an input, and then outputs a prediction of the incremental loss Y. We're going to have lots of models to choose from, so we need a criteria to select the best one. The criteria we've used is to minimize the expected average squared difference between the predictions and the actuals. And this is quite a general setup. So you have a measurement of closeness to the target called the loss function, and you're seeking a model that minimizes this value. So the loss function is actually a choice that's available to you as the modeler, and there are alternatives that are being looked at. So for example, it's reasonable to prioritize stability in your reserve estimates, and there are loss functions available that try to prevent large swings in the ultimate as models are refreshed for new data. Notice also here that we have accident and development period as features, but the beauty of this setup is that you're not just restricted to these two. So for example, you could add columns in here for accident year exposure or the prevailing Ogden rate, a weather index. You could explode the table out into subsegments and add that as a column. So lots of possibilities. Okay, so the next 3 slides capture what I think are the important ideas you need to know that differentiate the machine learning approach from a more traditional one. The first is features. So building good features from raw data is where you can add serious value with this approach. Machine learning has to work alongside active data management. Data is food for these algorithms. So to paraphrase the researcher Andrew Ng, even a star chef can't make a nice meal if the ingredients are moldy. So looking after your data and keeping hold of consistent high quality features is essential to getting value from this. So fancy models are useful, but you're probably always better off spending time on improving the data understanding the data than you are on tinkering with a model. And here's an example that's taken from the book Deep Learning with R. So imagine that you want to train a machine learning model that tells you the time. So one approach would be to feed thousands of images of clocks with labeled times against them into a huge complex neural network. So the input here would be a matrix of color values for each pixel. And that would be a time-consuming and quite a complex task to fulfill. A big improvement here would be to introduce two new features into the data set, which are derived from this raw data, called the angle of the hour hand and the angle of the minute hand. With these two new features, the model then becomes a lot simpler to train. So by focusing in on these two angles, you're helping the methods focus on the parts of the data that matter. And if we just look quickly at this table again, and it will become obvious when you see some of our examples later on, that adding a column here called calendar period would be a good idea, a good example of feature engineering, as it will help the methods pick up on calendar trends. Also worth saying, if you have a GLM background, you'll know that adding too many features here can become a problem as the fit becomes numerically unstable. This problem is much reduced for some of the algorithms we're looking at. So while it's still better not to include lots of pointless features, it won't break the process if you do. The Lasso and XGBoost algorithms will try to discard redundant features during the fit. The next important idea is hyperparameters and tuning. So most machine learning methods will actually give you a whole family of models to choose from. And there'll be a spectrum of flexibility or capacity. And this flexibility is controlled by one or more hyperparameters. And a bit like a volume control on an old-fashioned radio, the hyperparameter can be turned up or down, and the end result is a more or less flexible model. Finding the optimal value of that hyperparameter is called tuning the model. So here's an example. So here the white circles are from a quadratic curve where we've just added in some random noise. We're going to fit a polynomial to these 20 points and then use that model to predict the value at x equals 21. So this will be our test set. You can fit a series of polynomials of different degrees and then think of the degree of the polynomial as a hyperparameter. So if we start at one extreme, if you set the hyperparameter to 1 and fit a degree 1 polynomial, then you'll get the straight line model shown here. And this model is just not flexible enough to capture the quadratic curve in the data, and it performs poorly over here on the test example. And so this is said to underfit the data. As this hyperparameter is then turned up and we add more terms to the polynomial, the model becomes more and more flexible. And if we take this other extreme here and fit a degree 10 polynomial, you can see that this curve fits the training set the most closely. It's tracking the white dots very well. But when we then move into our test example, the prediction is just disastrously out. And the downside really of this flexibility is that the model is overly sensitive to noise in the training data set. And this is said to overfit the data, therefore. You can get a feel for what goes wrong here if you look at the fitted coefficients. So if you type 21 to the power of 10 into your calculator, you'll get a number that's about 17 trillion. And so tiny changes in this degree 10 coefficient have a huge impact on the prediction from the model. This high variability of predictions is characteristic of models with more capacity. So you may be thinking, well, it's fine here to say that the predictions for the flexible model don't generalize well, but we have access to the test set in this example, so we're cheating in a way. How can you use a data-driven approach in practice to prevent under or overfitting when you only have access to the training set? And this is where the third idea, the powerful idea of cross-validation, comes in. So what do? We withhold some training data from the fitting process. So you hold back some of the data from the fit, and you're then going to use that data to estimate the test error, estimate the performance of the model out of sample. So effectively, you're going to create a pseudo test set to use to test the model. There are lots of ways of going about this, and it's a key judgment in the machine learning pipeline. Here, we're just going to look at one of the more simple approaches, which is k-fold cross-validation. And here I'm going to use it with k set equal to 3. So what we do is we take our reserving data set from earlier, and then we randomly assign the training rows to one of 3 what are called cross-validation folds. So this is just a grouping of the data, a random grouping into 3 sets. We're then going to put, say, fold 3 completely to one side. So we're going to remove that from the training data and then fit the model on the remaining data in folds 1 and 2. We can then use our data that we've put to one side in fold 3 to test the model. So we fit our data on the available folds 1 and 2, and then we're going to estimate the test error by looking at the performance on this third fold. And so the process here is you have a list of candidate hyperparameters. So in the previous example, this would have been a list of polynomial degrees from 1 to 10. You iterate through the list and fit the model on the folds 1 and 2, test the performance on fold 3, and then you can select the hyperparameter which just had the best estimated test error. So you're effectively sacrificing some of the training data to help tune the hyperparameter, and that's with a view to finding models that generalize better. A way of thinking about this is to imagine that the available data is a budget, and how you choose to spend that budget is completely up to you as the modeler, but you need to allocate some of it to fitting the parameters of the model and some of it to tuning hyperparameters. It's just worth saying quickly that I mentioned there are lots of different ways of going about this. There is a particular cross-validation approach that the working party is looking at, which we think might be more appropriate to the reserving problem. And this is called rolling origin validation. So effectively, instead of randomly allocating the data to cross-validation folds, the data is allocated according to which diagonal of the triangle it sits on. And that's meant to then give you a better mirror of how the data is actually split, train and test in the real world. So that's 3 key concepts there: features, hyperparameters, and cross-validation. So next we'll just have a quick look at the 2 models that we're going to use. So the first is the lasso. And the lasso you can think of as a family of GLM models, which is indexed by this lambda hyperparameter. So for each lambda, we fit a beta for each feature X, and then our prediction takes this format here. So the bigger the beta, the bigger the influence that feature has on the prediction. And when a beta is fitted to the value of 0, that means the feature's got no impact on the prediction. So it's effectively excluded from the model. The number of features that get to be included is effectively controlled by this lambda hyperparameter. So you'll notice that because this is a hyperparameter, it doesn't appear in the prediction equation here from the model. So it's not a parameter that's fitted when you're fitting the model itself. It's a hyperparameter that needs to be tuned outside of the main model fit. So our aim is to find a lambda hyperparameter and a set of betas that minimize this expression here. So just breaking this down, the first term is the usual log likelihood from GLMs. So bigger values here mean a better goodness of fit. The second term here is what's new. And this has the effect of penalizing the model for including too many features. And this is a general technique from machine learning called regularization. So if you think of it again at the extremes, if you set lambda to 0, then you're just minimizing the log likelihood. So that's equivalent to fitting a GLM and including all of the features in the model. So that's the most complex model available here. And that would be more prone to overfitting. At the other extreme, if you set lambda to be a really large value, then this overall expression is going to be minimized when all the betas are set equal to 0. And so that would be the null model, the most simple model available, and that's more likely to underfit. So somewhere between those two extremes, we hopefully hit the Goldilocks zone. Another way of thinking about this is just to imagine that lambda is like an entrance fee to the club. If a feature can't afford to pay the entrance fee, which here means improving the goodness of fit by a certain amount, then it's set to 0 and not allowed in. The next method we'll look at is XGBoost. And XGBoost is a method you can't really ignore. So it's got an outstanding track record in data science prediction competitions. So since this was released in 2014, pretty much every winning entry in the Kaggle competition platform that uses tabular data has made use of this method. It's also a bit of a black box though. So for the lasso, you could follow the equations through and probably implement it in Excel if you wanted to. You're not going to code up XGBoost in Excel. It's highly sophisticated, a very highly optimized algorithm with several hyperparameters. The base model underneath XGBoost is quite simple though. It's a decision tree. So we've got an example here on the left. So if we were, say, predicting the incremental paid in accident quarter 25 and development quarter 10, then we'd start at the top of the tree. Is the accident quarter bigger than 20? Yes. Is the development quarter bigger than 30? No. And our prediction would be 32 million in this case. So you can see that's quite a crude way of getting to a prediction. Individual decision trees often perform quite poorly. The XGBoost method builds and combines a whole collection of decision trees. And the key insight is that you can get strong models by combining lots of weak models. This wisdom of the crowds type concept is part of a wider technique in machine learning called ensembling. So if you've ever taken a weighted average of different methods to select a reserve estimate, then ensembling will be familiar to you. The way the trees are built uses a concept called boosting. So successive trees are trained on the residuals or errors of previous trees, which forces later trees in the collection to focus on areas where previous trees struggled to get a good prediction. So the idea is that as trees are added to the collection, wrinkles in the aggregate prediction are ironed out. The dilemma of working with a black box model like this in a highly regulated environment and the whole explainability problem is probably a talk in itself, and the Working Party are looking into this as part of their work. So that's our framework, and now we're going to apply this to some data. So we're using simulated data so that we can, one, see the performance on the test set, and two, control trends in the triangle. So we have a simulator available that accepts distribution inputs for all of the key parts of the claims lifecycle, and then outputs payment level data. For this exercise, we've then aggregated that up into triangles before we've applied the models. So the simulator we're using is a package in R called Synthetic. There's a link to the documentation down here. It's a really good package. It's been built specifically for simulating insurance claims. And you can see on the previous slide, there's a lot of flexibility around the assumptions you can input. So it's a really good environment for creating test data sets. And there's also 4 interesting environments already in the public domain, which we've used in this presentation. And to try and see how volatile the methods are, we've simulated 20 triangles for each environment, and just by varying the random seed. So here's our environments. For each, I'm just showing here the paid development plot for 4 out of the 20 simulations. And then I've restricted it to 3 accident periods just to give a flavor. So the first environment is a simple short tail book with a consistent development pattern. So let's call that one Chain Ladder's Dream. Environment 2 is Chain Ladder's Dream, but with a rude awakening. So here we've taken the incremental payments from calendar quarter 30 onwards and uplifted them all by 30%. So that's intended to mimic a change in the external environment, say a change in the Ogden rate. Environment 3, Chain Ladder Sleepwalking. This is mimicking a social inflation scenario. So from calendar quarter 30 onwards, we've added excess inflation of 20% per year. Environment 4 is a gradual increase in claims processing speed. So there's no consistency here in the development pattern over time. So this is Chain Ladder's Nightmare. And then environment 5 mimics a longer tail book with more volatile claims development. So Chain Ladder Tossing and Turning. So in summary, we've taken 20 simulations of a 40 by 40 accident development quarter triangle. We've fitted a volume oil chain ladder and then a basic lasso and XGBoost model where we're just using the accident and development quarter factors as features. We've used 5-fold random cross-validation to help select our hyperparameters. There's more details on how we've tuned the lambda in one of the blog posts about the lasso method on our blog site. For XGBoost, we've just tuned the number of rounds hyperparameter, as we found that made the biggest difference to changes. And we've then fitted 2 what we're calling extra models, so lasso and XGBoost extra. So these are just the exact same models, but we've added some additional features to the table. The approach for having those features, there's more detail again on this lasso blog post, but it's things like interactions between the different development periods, adding on a calendar period feature, and so on. A final note of caution, this is by no means meant to be the final say on any of these methods or the approach. We just hope it showcases their potential. I don't believe that machine learning, at least currently, is a push button exercise. And there's many judgments in here that materially affect the prediction, such as the choice of your loss function, cross-validation approach, the feature engineering, which hyperparameters you tune and how you go about that. So many judgments involved. And of course, real world data hardly ever looks this nice. So that's going to introduce all sorts of other problems. Okay, with that caveat in mind, let's move on to results. So for each environment here, this table is summarizing the average reserve error across all 20 simulations. And then I've just highlighted for each environment which model gave the lowest reserve error. So I'll quickly run through those. So for environment 1, which is the simple and short tail triangle, the chain ladder does well as expected. And most of the machine learning methods managed to reproduce that. In environment 2, the calendar year effect starts to impact on the chain ladder estimates. And the 2 machine learning methods with the calendar feature managed to make use of that and perform quite well. Environment 3, interestingly, all the methods seem to underproject here. The Lasso and XGBoost extra models less so, with the Lasso doing a decent job. And then environment 4, and this is disastrous for the chain ladder, by design. The extra models again do quite well at utilizing the extra features to adjust for the changing claims processing speed. And then finally, the longer, more volatile book. Here, the machine learning methods seem to be slightly less distorted by the volatility than chain ladder, and the basic Lasso model does the best job here. So I'll now pass over to April, who's going to dive into these results in a lot more detail.
Hi, everyone. Can you hear me all right? John, you can hear me?
Yep.
Great. I will share my screen. So John has done the hard work of explaining how to fit the models and tune the hyperparameters to get a set of results. Now I'm going to go through the easy bit, which is to look at some of these results and start making some observations about them. Now, we all know that reserving is not just about getting a number at the end, but also about getting business insights such as emerging trends or unusual movements. So when we look at the relative performance of different methods, we've looked at also a range of diagnostics to assess whether these models capture those insights well enough, as well as getting more accurate reserves at the end. So I'm going to use scenario 1 on this dashboard as a starting point to explain some of these diagnostics we've looked at. And I'll quickly go through the remaining scenarios to focus on where the diagnostics tell us something more interesting. So we start off with cumulative pay development charts, which if you're a reserving actuary, you should all be fairly familiar with. On this screen here, we have 6 different charts. The top left corner chart is showing what's the cumulative claims development for the underlying simulated data. So almost the correct answer, if you were to think about it. And in scenario 1, we're talking about a very simple short-tailed claims profile. So all of the development profiles across the accident quarters are very tightly gathering around each other. So the remaining 5 charts show the fitted claims development pattern from the different methods, where you are using a chain ladder method and a basic Lasso method. Generally speaking, you are fitting a unique claims development pattern across all accident periods. So there's only one line going through the chart. And in this case, actually, given the tightness of the distribution of these claim developments, these 2 models pretty much do the job. Now, the other charts down here with the Lasso extra model and the 2 XGBoost models start showing a little bit of variation in the claims development, but only very tiny. For XGBoost, even the basic model showed a little bit because of the structure of the model, because XGBoost by essence is a tree-based model rather than a GLM type model that's controlled by parameters, prescribed parameters. So that's more likely to give you variability in the result than, you know, something like a lasso or GLM even. So that's cumulative development patterns. The second thing we look at is the percentage forecast error produced by the different methods. Now, the measure here we're looking at is the same measure that John showed everyone a minute ago, the difference between the forecast reserves as at calendar quarter 40 across all accident quarters against the reserves that were per the underlying simulations. And what we've shown here is the summary of all of those percentage errors across the 20 simulations we've run for each scenario, and the different bars show you the result across different methods. So you can see here that on average, all of the methods produce reserves that are fairly close to the underlying simulations, except for the lasso basic model, which seems to have been subject to over-reserving slightly, probably because of the heavier tail that it has fitted. So that's the percentage forecast error chart we look at. Then some of the scenarios we've looked at are about calendar year effects. So we've developed this diagnostic chart that shows you the average incremental payment at different calendar points for the entire portfolio of Triangle. And we've shown it for all the 10 out of the 20 simulations in this chart. And you can see all of them look fairly similar. So we can just focus on the top left corner here for simulation number 2. And you can see that the average incremental payment increases initially as you have more accident quarters coming into the triangle. But then it quickly becomes reducing over time, because as your claims are running off, the incremental payment made at each future point reduces. And then you have another further drop off at calendar quarter 40. This is the point in time where you have no more new accident quarters coming into the triangle. So from this point onwards, everything is in runoff, and therefore you have a much faster slowing down of the much faster reduction of the incremental payments over time. And I want you to remember the shape of this chart because it's going to look quite differently for later scenarios where we have calendar effects going on. And very quickly, lastly, we also have a chart that helps us to assess whether there's any accident year impact going on. So these charts again show the same thing across 5 different random simulations. So if we look at the first simulation, it shows you the incremental payment as a percentage of ultimate at different development quarters. And for each of those development quarter, the x-axis is accident quarter. So if you have an accident year effect going on, you will see an increasing or reducing trend rather than a roughly horizontal line like what we are seeing here. And because in this case, you're seeing a horizontal line, we can almost say that there's little accident year effect going on, which is in line with the tight cumulative claims development pattern we've previously seen. So in summary, we've looked at 4 different types of diagnostics. We assess how well the different methods capture the claims development profile compared to the underlying simulations. We also look at how well the different models actually are at forecasting the reserves in numerical terms. And then lastly, we look at how well the different models capture calendar and accident year effects. So without further ado, let's move on to the next scenario, which is where you have inflation, 30% uplift in all claims payments from calendar quarter 30. Now I'm going to show you the calendar effect chart first, because this is the chart that shows you the difference the most. And that uplift there, you can see at exactly calendar quarter 30 is the 30% uplift we're talking about. But because it's a straight uplift for all future payments, it actually didn't change the shape of this chart after that point. So literally everything just got shifted up by a nudge. Now, what does that also do to the cumulative development patterns? I think that just is going to lead to a slight slowing down of the patterns, but we'll come to that in a minute. Before we move on, let's look at how well these different methods perform compared to the underlying simulated data, which is the black line on this chart. So if you look closely, the purple, orange, and the green lines, which are the chain ladder method, the basic lasso and the basic XGBoost methods, seem to all missed that blurb at calendar quarter 30. However, the red and the blue lines, which you can't really see clearly on this chart because they mimic the black chart very well, are the lasso and XGBoost extra models actually captured that calendar year jump pretty well. This is what John was talking about earlier about feature engineering. By having those extra features that would represent those calendar year effects in the modeling, you will be able to detect such trends much more quickly and more reliably, sometimes even more reliable than potentially using humans' eyes. Now, going back to the cumulative development pattern, as I said, the uplift has led to a slight delay of the claims development pattern over time, but not too much. And you can see that, again, the chain ladder and the two methods with only the basic features were not able to capture that slight slowing down very well, whilst the lasso and XGBoost extra models were able to capture those pretty well. And how does that translate into reserve estimation error? You can see on this chart that the two models that perform the best are the two models with the XGBoost with the extra features, whereas all the other models tend to have overestimated the reserves because they probably overreacted to the 30% uplift at calendar quarter 30. So that's scenario number 2. It's still quite a relatively simple scenario, and you can see most models do cope relatively okay. Now, scenario number 3 is potentially the most relevant scenario for us now, because we're going through a period of high inflation at the moment. This scenario, we're assuming a 20% superimposed inflation after calendar quarter 30. And because it's inflation, so it's a compounding effect. And as a result, when you look at the incremental payment chart for this scenario, it actually changed the shape of the chart completely. So instead of having only one peak at the beginning, it has another peak at around calendar quarter 50 or just after calendar quarter 40, which shows you the effect of inflation coming into play. Now, the reason why it's not peaking at 30 but 40 is really because between calendar quarter 30 and this period, you have two offsetting things going on. One is claims being run off over time, and the other one is inflation coming into play. So I think it's only by the time you get to calendar quarter 45 or 50, really the inflationary impact peaks at that point or dominates. How well do the models perform? Well, you can see actually most models miss off the peak in most simulations. Even the XGBoost model with the extra features, the blue line, missed off the peak. The only model that seemed to have caught the peak pretty well is the Lasso model with the extra features, so the dotted red line, and it's consistently performed well across all the simulations we're looking at. Now, the reason why XGBoost model in this case, even with the extra features, hasn't performed well may well be because we're not tuning the model sufficiently, because as John said earlier, we've only tuned it on the number of trees rather than any of the other hyperparameters that might be available. So it doesn't necessarily tell you that XGBoost model is worse performing, but it does say that if you want it to perform well, you probably need to tune it a bit harder in situations like this. But we will see later on where there will be cases where the XGBoost model actually performs better with the same amount of tuning. So that's the two scenarios with the inflation or the calendar year effect sort of going on. We're going to look at something differently now. So when we look at scenario 4, this is where there will be a gradual acceleration in claims processing speed over time. And what does that mean? It means that actually it's probably easier to look at the cumulative development chart first, because that's the one that's easiest to explain. As you go along the accident quarters, the cumulative claims development pattern shortens over time. So you can see the trend going that way. And how well do the models capture that trend? Again, the two models with the extra features seem to capture the trend well, whereas the other models with only basic features, or the chain ladder model, only fitted one line. So by definition, it's going to miss that trend off. And when then we switch back to the chart that really examine the accident year effect, you can see here that across different accident years, you have increasing claims development at earlier development quarters, and then correspondingly reducing development across accident quarters at later development quarters. And that's true for all the simulations we've run. So how well do the models capture these? Again, the simple models and the chain ladder model all assumed a pretty flat incremental payment pattern over accident quarters. So they miss off that trend. Whereas the Lasso and the XGBoost models in these cases capture the increasing and reducing trends. But in this scenario, the XGBoost model seem to be the one that capture that, follow the black line much better than the Lasso model. The Lasso model seems to have some over estimation of the payment of the development percentage towards later accident quarters. You can see here. And what does that mean in terms of the reserve estimation error? As expected, the models that perform best are the Lasso and XGBoost models with extra features, with an average estimation error of almost near 0%. And even between those two, again, similar to what we've observed, the XGBoost extra model seem to be the one that consistently perform reliable reserve estimations. Now, we'll move on to the last scenario, which is a long-tailed, really volatile claims profile. This, in my view, is the only scenario we've looked at so far that is realistic, because all the other scenarios assumed fairly consistent patterns that you can even detect by eye, whereas for this one, you just can see that there's no clear pattern to the claims development, and the tail even the tail development is very hard to predict as well. So how well do the models perform in terms of capturing that difference and volatility? Again, simple models, we won't expect them to do very well. The Lasso extra model seemed to have captured some degree of volatility, but not as much as the XGBoost extra model did. Although personally, I feel like the XGBoost extra model may have slightly overfitted a little bit and picked up some noises, or potentially one might consider outliers in the data. In terms of reserve forecast error, now this chart is really out of scale, because you can see that the chain ladder method is really unstable in this scenario and can sometimes produce significant over reserve. So if we zoom in and ignoring those outliers, you can still see that on average, the models with the extra features tend to produce percentage errors that are slightly more closely. Sorry, these are the XGBoost models actually. So XGBoost models tend to, in this case, give reserves that lie on the lowest side of the the scale, whereas the two Lasso models tend to produce reserves that tend to err on the higher side of the scale. So that's one more interesting observation we've made. Also, in this case, even though the basic models did not capture the volatility or the range of cumulative development patterns in the data, they do seem to perform slightly better compared to the extra models, which might have been prone to overfitting in this particular scenario. So again, it's a lesson to be learned where it's not necessarily that every model would, there would be one model that performs always best in any situations. Hyperparameter tuning, feature selection, and sometimes even potentially averaging between models would be sensible ways of potentially getting more reliable answers. Now that's all I wanted to cover for this session, and I'll flick back to our main slides so we can go to conclusions.
Thanks for that, April and John. I can't say I got everything there, but I'm definitely need to kind of sit back and kind of work through it. I think there's a lot of food for thought there, even for a dinosaur like myself to go through, but I think it has shown that there's a lot of potential here that we probably should be starting to kind of bring into our kind of daily working life. So we'll just switch on to some Q&A now. And now I know I think I said at the start that we would have the raise hand function. I'm just looking at the bottom of the screen and that may not be turned on or available, but we do have a Q&A facility there. So if people do want to put in some questions in the Q&A, I'll monitor them and pass them over to John and April. That can be, you can do the Q&A with your name, or it can be anonymous if you don't want to share your name. Either works. Just while people are thinking possibly of how to, or what questions you want to ask, we'll kind of revisit something that we glossed over at the start, but we will We will share these slides, and within those slides, we will see our competency wheel. So you'll see that we've covered the kind of key skills of data analysis, modeling, and communication. We've also done judgment and functional expertise. So that's the kind of topics for completeness that we've followed today. So what people might be coming through with some questions. So we'll just ask one question, I suppose, to probably both John and April, and feel free to jump in, which whoever wants to answer it. But I guess one of the questions we have around machine learning is the black boxes. And it's always difficult to explain reserve movements, but how do you explain the outputs from a black box using those kind of machine learning techniques? Have you come across in practice?
Okay, should I go first? Yeah, I think that's a great question. It's a whole topic in itself, really, isn't it? Personally, I think the whole explainability problem is a little bit over-egged in this space. So when I think of explainability, I think chiefly of explaining why your model outputs moved, i.e. why you want to put reserves up or down. And, you know, your traditional tools that you have there around your percentage developed curves, your AVE metrics, partial dependence plots, they're all still available in this setup. You just be taking the outputs from the model. And one sort of advantage maybe is that there are some more modern explainability metrics that attach to these methods. So one that's come about fairly recently is SHAP values, which try to tell you at a very granular level how important an individual feature is. So if you check out our blog site, there's an example with mobile phone data where the SHAP value, it visually shows you quite nicely how important, say, development factor period 2 is versus whether the phone is a certain brand. April, anything to add?
No, I think the examples John has given would certainly help with explainability. The thing I would add is the reason why we developed those R dashboards was exactly because we wanted to show people that by looking at fitted or modeling results in graphic ways, you could also get insights out of what these models have done without having to interrogate into the modeling details as much. So that's just something else people could do to help increase the explainability of some of these models as well.
Change of tack a little bit, I guess, for most reserving actually, potentially the hardest part of the job is probably getting the data ready and going through the data aspect of before we even start looking at the kind of analysis. But what's the main limitation of adopting machine learning to predict your first kind of reserve numbers for when you go down the machine learning aspect of it? Because I assume the data is still the same, but then what is the biggest problem after that?
Yeah, for me, I think it's back to that survey where there's a lot of appetite for this, but it's currently lack of time and a skills gap. So, you know, you do need to invest in coding skills to have a dabble with this stuff. So picking up R or Python. And I think until the benefits are kind of proven, it's quite hard to make a case to invest time in this kind of stuff. So that's why I would recommend starting small. You know, maybe you have a book where you're doing a deep dive and you have some good granular data, and maybe you can try applying a machine learning technique, see if it tells you anything interesting about trends or features in the data. And then once you can prove the benefit to the business, it's easiest to then make the case to invest more time.
Mm-hmm. And another question I had thinking through this was, and I think it might be similar to one of the Q&As we have, is that does this method of machine learning and reserving tend to lend itself better to some types of business rather than others? like certain portfolios, I'm assuming the more data rich classes will be more applicable here, and possibly the longer tail. But as well as that, does it kind of also related be, does it respond equally well to paid and incurred claims data, or is there a difference there?
Yeah, so we use paid data for this talk, mainly because the simulator we had available only did paid at that point. That's now been extended to include incurred, and we are also looking at some real world data where we have the incurred as well. So I'm not sure how it looks yet, but I think it will definitely be possible to apply it to incurred, and that really is a prerequisite before you can use these methods. I think you have to be able to utilize the incurred data. In terms of where it works well, again, I think it's still early days to say one way or the other. I think potentially there's two areas where these methods can really help. One is where you have lots of data and you want to pick up trends more quickly and more reliably and more granularly. But the other, though, might be, say you have a sparse class, maybe it's tempting sometimes to see a pattern in the noise in the triangle. And some of these methods, the way the cross-validation is designed is to try and not fit to the noise. And so you might get an interesting challenger model that gives a different answer to what you would pick by eye.
And you might have covered that there, John, but there's one particular question that's come in there around, has there been any consideration or research that examines which of the models performs better or worse where one is training the model to sparse real world historical data? And I guess that question is more focused on which of those kind of machine learning techniques is better in that situation.
Yeah, and again, and I know I'm saying, it's early days, don't have all the answers yet, but it genuinely is early days. So I'm not sure yet. I mean, they perform better with more data. You have to be careful of taking it too far, because there's still going to be room for judgment in all this. There's still going to be trends in the future, and you shouldn't lull yourself into the idea that machine learning is going to solve that. So, we take inflation, for example. No matter what data you feed into a machine learning model or how granular, it's not going to tell you what's going to happen with price inflation in the next few years. And so you're going to have to make a judgment about that.
Okay, and I guess that's one clarification, because you were talking through the various scenarios with the inflation shock, and I was trying in my own head thinking, is that a kind of past inflation shock, or is that a future inflation shock? And then how does it actually model? How do you allow for the potential future inflation shock that may not be kind of, you may not know about it and you have to project? And is that similar to the way we do things at the moment, in that it's really just making a judgment call, or do you allow the model to do that automatically?
Yeah, so I think for that specific example, the idea is that the method would react to the past inflation perhaps more quickly than a raw chain ladder. Well, if say in that example, I think we had inflation like 20% a year, say that suddenly jumps up to 100%, but it's after the period where you've got some data, then you would have to be making an adjustment to allow for that. So yeah, it's really picking up past inflation.
We have another question here that's similar to something that I did in a prior life, and rather than trying to reserve using kind of portfolios and incurred claim data, you kind of reserve maybe more so on individual claims. And is that something that is being considered about how you might move away from the whole kind of maybe accident year to kind of start doing deal or kind of claim specific reserving?
Yeah, that is definitely being looked at by the Working Party and others, and it absolutely makes sense, because if you can get down to that more granular data, you can get more out of these models. So there's a good example actually on Kaggle called the Actuarial Loss Prediction Challenge, where it was a big long list of workers' comp claims, and you had things like whether it was a male or a female claimant, and whether they were part-time, full-time, their wage, category of employment, things like that, and you could test machine learning methods to see how well they would predict the settled value based on those features. So yeah, I definitely think that's an area where it's ripe for development.
Mhm. We have another question for explainability, and I'll give John a pass, and maybe April, if you can have, have a go at this one. I guess the question is, how easy is it to perform a quarter-on-quarter comparison between two sets of model outputs? Does the working party have any examples where they've done such a comparison?
Sure. Can you hear me okay?
Sure, yeah.
Yeah. I think this is an area that we are starting to look at, particularly for explainability in a wider context for any sort of data science or machine learning related type development. So we have a active group of our working party, so machine learning reserving, and there's a data science working party. And I think we're jointly looking at, and particularly the data science working party is looking at explainability of new methods. At the moment, there hasn't really been a set of predefined method comparison sort of metrics. As I said, at the moment, what we've done is looking at diagnostics, and you can turn some of those diagnostics into very summarized sort of KPIs or comparison benchmarks for your quarterly process. I think really we're still at the stage where we're trying to encourage people to apply machine learning methods on real data, or think about doing them. At this stage, personally, I would hold a very open mind to any method and just see how well the methods perform in comparison to, say, how you would expect a human experienced reserving actuary to have reserved in some of those situations. There isn't really a predefined set of metrics that we can apply on to say, you know, if these models perform well in these 1, 2, 3 KPIs, they are a better model versus a worse model. I think that's still an active area of research that's ongoing, and it's only when we accumulate sufficient experience in applying these models in real life data can we start concluding about some of those comparisons.
Yeah, I think I know the answer to this one. I think, John, you might have mentioned this somewhere in your presentation, but what is the real kind of benefit, I suppose, and what is the sales pitch to kind of get companies and get CFOs to sign off on moving to a kind of machine learning technique? Is it the kind of saving of time, or is it kind of more accurate numbers, or just more information to base you to kind of estimate your numbers on?
I mean, for me, I quite like this concept of challenger models. So once you've set this kind of code up, it's very little time to run it. And I could see a use case for, you know, you have a machine learning model, you run it, it gives a vastly different answer than what you're selecting using your traditional approach. And the machine learning method saying, you know, these calendar features look like they're exhibiting a trend. Then that would be useful information for the reserving team to then maybe have a look at the current estimate and think, is there something else going on here? And the other side of that coin is what I mentioned before about, you know, maybe sometimes there's a temptation to see a pattern in the data. Machine learning challenger model might tell you how robust that pattern fit is, and maybe say that you found a trend that the method just thinks is noise, and that again would be useful information. So for me, it's principally kind of trend identification and a sort of an extra tool for the actuary to use in the reserving process. I don't know, but there are different. I don't know if you got anything to add to that, April.
No, I think I agree with what you've said. And also, I think it's an area where it's changing by the day and by the week. So even starting somewhere and starting to get on top of the new stuff that's coming out and experimenting is at this stage for any reserving actuary in the industry, I would say is a good idea. For companies from a commercial perspective, a lot of it is not just about getting better reserves necessarily. It's also getting reserves faster and cheaper as well. So it can be part of a wider solution to make the whole reserving process better, rather than being a siloed, let's sell you a package of machine learning models and your reserving process is going to be amazing kind of solution.
We have one question. I thought we were going to go one webinar or one presentation without delving into the world of regulation, but I think we do have a question that's coming through about has the Working Party had any regulatory engagement on this topic? And I know in other jurisdictions, maybe around Europe, regulators are getting more involved in understanding what goes in behind models, whether they be pricing, whether they be reserving, and is that something that has come up yet?
I'm not aware that we as a Working Party have been speaking in particular to the regulator. I suppose one point I would make is that our colleagues in pricing are using a lot of these techniques already, so they're not kind of completely novel. It's just applying it in a reserving context that's maybe new. So hopefully they've done the heavy lifting for us when it does come to that regulatory engagement.
And some of our Working Party members personally have worked in regulators as well. I guess it's an area that's new, but at the same time, the regulators are aware that it's an emerging trend that everybody is looking at the same time. So I feel like at least now, from what we can see and from the kind of personal engagements we've had with people working with the regulators, people are generally holding an open mind to these new ideas rather than just going, oh, that's a bit uncertain and therefore we're not going to allow it or look at it.
Yeah, true. And I guess that the conflict may come in that there's probably more stringent rules on what you can do on the pricing side and what information you can and can't use in pricing, and maybe there's a gray area there when you move from pricing into reserving and how that's going to use going forward and what data is captured, etc. So it probably will be a kind of evolving space over the next few years. As you said, things are moving very quickly in the space. And that kind of brings up to and my probably last question I have is, it's really about how to, if someone really has an interest in this space, how should they proceed in learning more and getting more into the day-to-day aspect in this field? Because I guess we'd probably all have to do it sooner rather than later. Some of us are probably near the end, others are coming into the career, they'll probably naturally get into it. But how would you say someone should start finding out more of how to do this in real life?
Have I mentioned our blog site? Yeah, it's all Paul.
There you go. Advertisement.
Yeah. So yeah, we've got a getting started page on there. I'd recommend having a look at that. It gives a kind of list of resources. For me personally, I found there's a course by Stanford University. It's on a site called Coursera, so it's free to access. And it's by one of the kind of leaders in the field called Andrew Ng. And that's really good just for understanding the concepts, really informative and engaging lecturer as well. And then outside of that, I think it's worth picking up either some Python or some R code and then just try it on some examples. That's the way I find easiest to learn if you've got something you're trying to make work.
Mm-hmm. I guess the challenge for us all is how to squeeze that into busy day jobs.
Yeah.
So I don't think there's any more questions to come through. I think I've answered. I think I've kind of fed most of the Q&A to you guys. I think just all that's left to say is really thanks very much for a really interesting presentation. I think there was a lot to learn, and hopefully from that presentation, there's people there that will kind of take up this topic and go forward with it. But thanks again for the for a super presentation.
Thank you.
Thank you.
Welcome. See you guys.
Bye.